Right. So in the previous lecture we talked about pattern matching. In previous two lectures we talked about regular pattern matching first and how that worked and how to use it. And then we talked about active patterns, which is a way that allows us to actually program how pattern matching happens and write our own matchers, which can be infinitely flexible. A very nice way of writing clean and succinct code. Before we continue, I think it might be in order to take a quick look where we are in the course. So part one of this course was really the theory, where we talked about sort of formal things like lambda calculus and type theory and what is the meaning of these things. And now we are in the middle of, or towards the end of part two, which is F#, the language. What are the most important language constructs? And today we will be talking about recursion. And after recursion, we will look at collection types and recursion from a slightly different perspective again. And then we're going to turn our attention to look at the object-oriented features of F# and cover sort of the basics of how to do object-oriented programming in F# and why you might want to do that. And when we're done with that, we're going to do some miscellaneous debris, collect up little odd bits here and there that might be interesting. Exceptions and mutability is one thing that we're going to talk of before we talk about objects. And then just collect up a little bit odd bits in the end. And then that would sort of conclude part two of the course. And after that, we get to the real meat of functional programming. Then we're going to start talking about abstractions for real. And we're going to start covering things like functors and applicative functors and monads, or computation expressions as F# programmers like to call them. Continuation passing and various things. And see how these things are useful and where they are used and why. And this is super interesting because this is really sort of getting into the real machinery of how to do proper functional programming. And then after that we turn to the last part, part 4, which is going to be practical F#, and we're going to start looking at, okay, how are we going to write cool server client web applications and so on, and make things look nice and interact on the screen. So that's going to be the sort of conclude the whole thing. All right, so let's do recursion quickly. I assume that most of you are familiar with recursion, but in functional programming, recursion is really important. And the reason is that if we are doing pure functional programming, we don't have any variables, mutable state, and we can't do any looping. Because if you write for I equals 0, I less than 10, I plus plus in C, this is actually mutating this I variable, and that's not really a good idea. And if we don't have any loop variables that we can increment, then we need to do something else, and that else is recursion. That is, we call ourselves over and over and over again. And whenever we do recursion, we need two cases that we need to account for. And by the way, recursion is also how mathematicians loop. Like there's no loops in math, but you will find a lot of recursion. So we have two cases whenever we do recursion. Because if we just call ourselves indiscriminately, then we just will call ourselves for infinity. And we end up with an infinite loop, or until we run out of memory. So we have what is called a base case, which is essentially the condition where we stop. And we have the recursive case. These are the two cases that we have. And if you now want to write the recursive function in F#, and I'll just do the factorial because it's super easy and it sort of really nicely shows these things. So if I want to write this factorial function in F#, let fact take some n, and then we say, well, if n equals 0, then 1, right? Else n times fact of n minus 1. So this would be the factorial. So we come in here, we give it some n, say, so we say 5, and then we say, well, is n equal to 5? No. Then we go down here, and we take n, which is 5 times, and then we call ourselves again, but now with 4. Okay. So one of the problems we encounter immediately in F# is that we need to have everything defined. We can't use a function before we have defined it. So everything has to come in order. And now we have a little problem, because when we reach this point here, this fact function isn't defined. Has not been defined yet. We are in the process of defining it. And in order to tell the compiler that this is it needs to take special care with these things, we say let rec, to say that this is a recursive function. And now I can call myself. So, okay, so what happens here? We come in here, we hit this line here, we can compute n times, but this one we don't know. So we need to call this thing. What happens when we call this thing here is this gets pushed on the stack, a return point. We call this function, it goes in, same thing over and over and over again until we hit 1. And then we return the 1. So now what we get when we get on the return, when the function returns, this will return 1, and this would be 2, and then so we get 2, and then that returns, and we get 3 times 2 times and we go back. And on the return we do these multiplications because we cannot do them until we have computed this. And this is an important little detail here. So what happens is that if this n becomes very large, for every iteration we're going to push stuff on the stack, the return, what the arguments were, and so on, and then and pretty soon we're going to run out of stack space, and our program will crash. So this is a problem. It's very inefficient to push things to actually do real function calls, and we run out of resources. So people invented something which is just really a technique to make these types of recursions feasible for functional programming, so that we don't consume stack and that we can sort of get back to a normal loop. Because if you're a mathematician, you don't care about stack space. There's nothing to keep track of. You just do it in your head basically, or just they deal with infinities all day long, so it's no problem. For computers, infinities, yeah, a bit of a problem. So let's see if we can rectify this. So this is what we in this case is our base case, and this is the recursive case. Base recur, right? So how can we change this so that we can turn this into something more efficient? And we actually need to rewrite this function slightly. And the problem we have, and the heart of the problem, is this thing here. The fact that we need to call this thing, and then we need to do something with it on the return. So if we can change this last recursive, in the recursive step of this, if we could change this into such a way that the last and only thing we do is call ourselves, and then we don't do anything else. So that actually that when we start returning, all we do in every single return step is just pass back the final result. Then we can actually optimize away the whole thing. We can just say, well, we're never going to return back, and we're never going to unwind the stack, and actually we're never going to even push anything onto the stack. The compiler can do this in the background. It can just get rid of the recursion and just use jumps instead. Instead of using calls, it will just use simple jumps. It doesn't need to save anything on the stack. Right, so how can we turn this last step into something which doesn't push on the stack? Well, it's actually quite easy. I'm going to write the function here, let f, and it's going to take two arguments. One which I'm going to call acc for accumulator, and one which I'm just going to call it x. Right, and then I'm going to say if x equals 0, then we get to the base case. But now instead of returning 1, I'm going to return acc. So this is the result now. Instead of returning 1 and then start unwinding the stack, I'm going to return the result. And then I say else call f x times acc x minus 1. Right? So now I get down here with a new x, I multiply it with the current result, and then I subtract 1, and we go around until we hit the base case, and then we just return the value. And this will just go all the way through. So here we see that the only thing I do in the last line, the only thing, there's no like multiplication, add or anything. I'm not using the result of this thing. It just returns, right? So now I have a tail optimized recursion, and I'm happy, and as can be. So the only little nasty bit with this approach here is that now, if we look at any libraries with factorials, you would see something like this fact n, not fact acc n. So this is a bit sort of tedious. Why we get this extra accumulator here? So what you typically would do is you would say, okay, this is an internal function inside a function which I'm going to call fact of n, and this is an internal fact, and then I'm just going to call f with 1, which is the initial accumulator, and then n. So now I'm going to call this internal function, which is going to recurse, return the value, and I return it to you. And we have recovered a nice interface, right? And now we have something that the compiler can turn into a optimal loop, which is, there's no difference between a loop, C loop and this loop for the compiler. Right. So Simon is sitting here with me and listening to this, and he has a lecture very soon, so I'm just going to cover a quick little topic before he's off, and then we're going to continue. After that with the next topic. Right, so there's a little thing that we need to take care of. So sometimes we end up with this chicken and egg situation, where one thing is dependent on another thing which is dependent on the first thing. And how do we solve that? This is called mutual recursion. So let me show you what I mean. So we can do a function let f of x, and then I can say, well, if x is greater than 0, then what did I say here? Then call g of x minus 1, sum g, else x. And then I can say let g of g x equals if x is greater than 0, then f x minus 1, else x. I need to change this. right? So now I have this situation where f here is calling g, and g is calling f, and this one isn't defined here, and this guy isn't defined. Like you end up in a ugh. And then there's a savior, which is the mutual recursion. We can, instead of saying let, I can say and problem solved, right? Another example of this is for types. So suppose I have a type which would be type folder, and I have a path, which is a string, and I have contents. Yeah. Which is what did I call it? Yeah, I just call it contents. List, which is a list of items, right? So here the folder is something which contains, it's a path to the folder, and then it has some stuff in it, right? And this would be all good. And then, well, type cont here is a record type with a name, which is a string, and then it has a type which would be either now I'm gonna just do a little, I need an extra type here. Well, I can call it type, we just call it kind, which is either a file or a folder, right? File of some stuff, or a folder of a folder of a folder, right? So this is a type of this kind thing, what kind of a contents we have. And now we see again we have the same problem. This type here uses this cont, and this cont is through this thing is using that thing. So now we're again in the same problem. And again, instead of using and type, we use and. And now we can define these neutrally recursive data types, which can refer to each other back and forth, no problem. So that's an example of that. Okay, so, and in fact, you can make whole modules recursive. So you can say rec module, or is it module rec? I can't remember, I never used these. But you can say that anything in this module is basically applicable for recursion, which might be good if you have a lot of recursive stuff, so you don't end up writing all these and rec. Usually not recommended. And your compile times will certainly suffer if you do it, because compiler needs to work much harder for these things than for normal functions. All right. Simon is off to the lecture grounds, and we'll continue in an hour. All right, we're back. So before we conclude this section on recursion, there is one little piece we are missing. Now we looked at recursive functions. We looked at mutually recursive functions and types, but we can also have recursive types. So types which have recursive type definitions. And the canonical example of this, and this is beautiful, this is really beautiful. The canonical example of this is a linked list in F#, or Haskell or whatever. But so what we're going to have is a type called let. Type list of t. The list will be necessarily generic, equals, and we have two cases. We have the case nil, which means end of list. And we have the case which is commonly called cons of T, list of T. So now we see we have a case of this union type, which is a list of T, which is the type we are defining. Okay? So what is this list? Well, this is a list of pairs where we have a type of T, integer, comma, a list, which again is a pair of something, comma, something, until we hit nil, where it stops recursing. Right? Isn't that beautiful? This is a linked list. No pointers, no nothing. This is so nice. Like, can you come up with a better definition of a linked list than this? I doubt it. Somebody said that to loop is human and to recurse is divine, and this is certainly true for this case here. This is really fantastic. So let's see if we can encode a list and see how one would use this list. And by the way, this is actually how you define a linked list. Like, this is the real thing. So this is not like some. So let's see. Let's make a list of integers 1, 2, 3. Let L equals, right? So we have a cons, and it takes a pair. Now we can say 1, comma, cons takes a pair, 2, comma, cons, okay, cons takes a pair again, 3, comma, nil. This is the list which we also can write 1, 2, 3. Every cons constructor takes a pair. Here we have a pair of a something and a list, of a pair of something and a list, and a new list element until we hit nil, which doesn't take anything, and then you can't go on anymore. We're terminated. End of list. Also usually written as empty. Right? Okay, so can we use this thing? So let's write the function. Let's write the function which computes the sum of this thing, right? Let rec. I'm gonna recurse, of course. You don't know how many elements we have. And now actually I look here in my notes that I'm going to teach you a little trick. So I'm going to do let rec sum x equals, and now there's a shorthand for writing match, which is I can just write function. So this creates essentially a lambda function which takes a single argument and puts it straight into a match. So I can say this, and I can say pipe cons and then we have two elements, x and y. So if it's a cons, we know that we have an x, Or maybe should call this something else. Yeah, okay. I call this n instead. So I call this x and this xs. So this is a very common way of calling list x and the xs. Yeah, get it? xs. Huh? Yes. And we're gonna call sum, and then we put in the x plus n and give it the xs. So we're just gonna call this repeatedly. And if we hit nil, we're just gonna return n. Yes. Then we have a summation function. Right. So that was basically it for recursion and recursive types and deconstructing types. This function trick here is like, so maybe I should just do that once more to show what it means. So I can write something like let fx equals match x with, right? Usual thing. So I write a function called f, takes one argument, and then it will match on x. But then this is sort of this is a lot to type, and this is an extremely common pattern. So this occurs in so many places when you are typing code. So they found out that, well, basically you could say like this is f equals fun x, right? So we could just say replace this. We don't give any argument here. We replace it with the lambda function x, and then we match on x. But then this is also like not really. So what we can do is we can just skip this and instead write function, which is a shorthand for saying fun x match x with, and then we can just match our cases here. Very useful, handy little shorthand. Just pure syntactic sugar, but makes for readable code once you know it. There's bonus points for using it. Not. Right. So that was that. In the next lecture, we will talk a little bit about how to recurse without doing it. Until then.